Um, Hi everyone, welcome to today's COMET webinar. But before I start, I want to take the opportunity to advertise our next webinar, which will be on the 6th of December at 4 p.m. UK time. And during this, we'll hear from Ben Essie, who is a postdoc at Manchester, who will be speaking about what satellite measurements of sulfur dioxide can tell us about volcanic eruptions. Our speaker today is Jess Payne. Jess is a third-year PhD student at the University of Leeds, where she works with John Elliott, Mark Thomas, and Kate Donovan. Jess is part of the COMET LiCSAR project, which uses InSAR data to map regional scale surface deformation, and her PhD research involves mapping and analysing land surface subsidence across Iran using InSAR and other Earth observation data, which Jess will be talking about today. The talk will last for around 35-40 minutes with plenty of time for questions after. So if you have any questions, please put them in the Q&A and we will come to them at the end of the talk. Over to you, Jess.
Great. Thank you very much. And thanks for inviting me to do this webinar today. It's quite exciting. So I'm just showing my screen. Oh no, sorry, 1 second. I'll just start showing my slides. Is that okay? Perfect, thank you. So yeah, as Isabel said, I'm a PhD student at the University of Leeds, working as part of COMET and the LiCS project, and supervised by mainly John Elliott, and working with all these other people listed here, in an attempt to assess the subsidence-induced hazard across Iran using Sentinel-1 InSAR data. So firstly, thank you to Yasser, who's hosting this webinar, for providing this photo in the background, which is of a beautiful bridge across the Zayanda Rud River in Isfahan, a city in Iran experiencing quite severe subsidence. So hopefully that sets the scene a little for the rest of the webinar. We'll start with first an overview of what I'm going to talk about today. So first we'll start off with some background explaining what is land surface subsidence, where and why is the subsidence happening in Iran, and then we'll move through the methodology and the results which we've been working on recently. First, how we analyze and produce the time series data from the Sentinel-1 InSAR data, and then moving through, for example, comparing this results to land cover products, assessing the surface faulting risk, and finally assessing the contribution of fading signal or phase bias to these velocities. So firstly, the background. What is land surface subsidence or subsidence? It's simply a lowering of the land surface over time. So taking a look at this GIF here from the New York Times, as you can see, the water table is lowering over time, which is generally what causes subsidence globally. In most cases around the world, it is anthropogenic related, if we were looking at this sort of speed of subsidence and sort of geographic extent of the subsidence. But yeah, here this GIF is designed to show you what subsidence is like in Mexico City, hence the labels of clay and volcanic soil underneath buildings. But if you sort of change these labels to maybe clay, sand, a mixture of the two, this could really represent what's going on in Iran as well. Not all over the country, but in pockets where there is subsidence. Also to note, you can see the building sort of tilting and deforming as the land collapses, which is important. So the water table may look like it's kind of uniformly dropping over kind of a long wavelength, which is true. But the subsidence that happens at the surface, the pattern can be controlled by the sedimentary deposition underneath, leading to sort of differential rates of subsidence in space, causing this sort of tilting of the buildings caused by sort of hogging and sagging of the ground in more technical terms. So that damage to buildings is something we need to focus on, because that's some damage we want to know where it might happen and where it can be prevented. So more technically, what is land surface subsidence and how does it happen? Well, we talked about lowering of the water table over time, and this might happen because people need drinking water, fresh water to drink, and also to irrigate their crops and have food to eat. So when this water table lowers, pore water pressure decreases. And what does that lead to? So this equation here is the equation revolving around the effective stress concept. So here we have total vertical stress, which is the load upon the soil underneath the ground, which includes buildings, the weight of the sediment itself above that level, and that's equal to the effective stress plus the pore water pressure. So the effective stress is the load taken up by the sedimentary grains themselves, and then the pore water between those sedimentary grains does take up some of that load as well. But when you remove that pore water pressure, reduce it, it must mean if the load is the same, the effective stress increases. So the load taken up by the sediments goes up, which means over time, if you look at these yellow grains, one, the pore spaces between the sedimentary grains must sort of compress and squish. And also sometimes the sedimentary grains themselves can also deform and the sediment consolidates somewhat permanently. What this leads to is deformation at the surface, which we can observe remotely using satellites. We can also observe it on the ground, but satellites allows us to observe a large geographic area without having to go to the area in question in quite a short amount of time. So here we're looking at Sentinel-1 satellite, and it's sending out radar signal towards the ground at a line of sight angle to the ground. And you can see that red portion at the end of the green circle, that's highlighting where the land surface has gone down, and we can measure that with Sentinel-1 SAR data. We can also decompose that signal, which we record in the line of sight direction, into east-west in red on that little inset diagram, and vertical components, which we'll talk about more later. So why can land subsidence be a problem? This is something we alluded to earlier in that GIF of sort of subsidence in Mexico City, but we'll talk about it more here. So here we're looking at a map in Iran. On the background, there is an optical image showing the ground surface in this area of Iran, Rafsanjan. Here is an area that experiences quite rapid land surface subsidence. And this map on the left was produced by Madi Mortag in some great work in 2017. On top of this optical image, which shows a pistachio plantation in the northeast, you can see there's lots of colored dots across the image. Now what this means is this is InSAR data, which I was talking about earlier. And in the sort of bottom left of this image in the southwest, this is blue colored, these dots, and in the northeast, they're red colored. So the blue color shows the land is stable, it's not subsiding at all. And the northeast, it's subsiding vertically and going up and down, well, down 30 centimeters per year. And what this means there's a velocity gradient across this area of land in a southwest to northeast direction, which is quite steep. And what you can also see, pointed out by these white arrows across the image, are crack zones developing. Now, if we look at these in more detail, for example, this number 2 here, this is an image from the field taken by the research group back in when they did the work before 2017. You can see these are long linear features in the landscape that go on for quite some distance. Additionally, there can be quite wide sort of meter scale fissures in the ground. Now here, this doesn't cause much damage to infrastructure because there isn't any infrastructure here. But as you can imagine, if there were buildings and roads on top of this land, this might cause quite a problem. So something we were talking about, I said earlier, was the gradient of velocity across this scene, across this red line, if you imagine. Now you can measure this gradient with something called angular distortion. This table here shows some numbers in it, and these are values of angular distortion. And you can classify, we'll just talk about what that is briefly. So angular distortion is beta here in this equation, which represents the differential gradient of vertical velocity, so delta d ui. So basically the change in subsidence velocity over a distance of L. So on the ground, over how long is that difference in settlement happening? In this case, we're seeing 30 centimeters gradient in velocity, so blue to red, over about 0.8 kilometers or 80,000 centimeters. And this works out to be this number here, 0.000375. And if we look back at our table, if we classify angular distortion into different categories of surface faulting hazard, this works out as sort of a medium level of hazard due to this subsidence gradient. That doesn't seem too high, medium, but as you can see, there's still quite a lot of damage in the surface, cracks, long linear crack zones, which can develop. So here we mentioned if buildings are on top of this steep subsidence gradients, damage like this can happen to the buildings. So this is another location where rapid subsidence is a problem in the Linfen Yongchen Basin in China. And you can see there's quite severe damage to this abandoned building. Here the subsidence velocities sort of reach about 50 to 60 centimeters a year. Oh, millimeters a year, sorry. But it's the gradient of subsidence which is a problem rather than the peak absolute velocities. So we mentioned a few locations so far where subsidence is quite prevalent. China, Mexico City, and obviously Iran. But where else in the world can subsidence potentially happen? So in 2021, Herrera Garcia et al. Published this map of potential global subsidence, basically predicting where subsidence might be happening in 2010. As they construct this map. So first, they calculate global subsidence susceptibility, which is working out which land surface is susceptible to subsidence without taking into account what the actual groundwater levels are. Then combine this with the probability of groundwater depletion, so using groundwater depletion data to give us a better idea of where subsidence might actually be happening on the ground. As you can see, the red and orange and yellow colours are where they think there's a medium high, high, or very high chance of subsidence. And these areas concentrate in this sort of 30 degrees north band across the globe. So places like Northern India, China, around the Mediterranean, North America. And what are the reasons for this? One, this is like a climatically quite dry region of the Earth, same as the 30 degrees south latitude, but also there's more land here, so there's more likely to be people here. And additionally, it's the site of more densely populated cities and faster developing populations. There's a greater strain on the groundwater that exists on the ground. If we look at where subsidence is actually observed using InSAR, you can see it's quite a good correlation with the predicted subsidence. So again, around this 30 degrees north band, you see lots of instances of subsidence represented by these circles. Now here, the deeper the blue, the faster the maximum rate of subsidence observed in each of these studies. You can see there's some like hot spot zones for this phenomenon. So for example, San Joaquin Valley in California, Mexico City, Bandung in Indonesia, and again Shandong, China, and of course Tehran in Iran. Now, to give an idea of how severe this problem can get, or the magnitude of subsidence you can observe over time, this is a picture of Mike Poland from the USGS in 1977, who's sort of a pioneer of studying land subsidence in the US. So this is a telegraph pole in an agricultural plain in the San Joaquin Valley. And the base of this telegraph pole back in 1925, if it was actually there, would have been at that 1925 sticker on the pole. So that's representing about 9 meters of subsidence in 52 years. So you can see how drastic this land subsidence can be if it continues over quite a sustained period of time. Going back to Iran, what's the groundwater depletion status here? And why should it lead to land subsidence? So here is a map on the left of different plains across Iran, classified by their status of whether you can drill a well in this plain or not. So wells are drilled to pump out groundwater from the subsurface, and in these red-coloured plains, this drilling is critically restricted, so it's quite difficult to get permission to drill a well here. In the green areas, you can more freely drill wells. And to give more of a context about the groundwater depletion status in Iran, groundwater provides 90% of Iran's agricultural sector water needs. And over recent time, 2002 to 2015, the withdrawal of groundwater has decreased 18%. But at the same time, the number of extraction points has actually increased a significant quantity, 85%. So indicating the situation of groundwater underground. In a longer time scale, 1968 to 2008, total water resources per capita have decreased 65%. In Tehran, 30,000 or 50,000 miles are estimated to be illegal. So as well as the groundwater level on the ground dropping and becoming more difficult to access, indicated by the statistics here, monitoring the wells that are around the country, particularly in Tehran, for example, is difficult, as many of these are illegal. So back to subsidence. We know about the picture of groundwater depletion in the country, but back in 2008, Madi Mortag was one of the first to, on a widespread scale, calculate and work out where subsidence is happening across the country. For example, in these 6 areas, he published data showing subsidence and how fast it is and where it's happening. He was then linked this to water level changes in these areas and was the first to really relate that groundwater depletion that we talked about to land surface subsidence. Since then, there's been a really rich body of literature, mainly coming from Iranian scientists, building on this work and really building a picture of land surface subsidence across the country. So this map here shows Iran, in the background, a topographic map based on a digital elevation model from COP30, called COP30. On top of that, we plotted in black the active tectonic faults in the region. And on top of that, in brown, we are outlining, based on our studies, where we believe subsidence is happening in Iran over a velocity of 10 millimeters a year. So inside those brown polygons, you're seeing quite fast subsidence. And to give you an idea of where current studies have focus, these blue circles show the sites of these previous studies, and the color of the circle indicates the maximum velocity observed in each. You can see there's quite a good coverage across the country of studied subsidence compared to where we believe it is, according to our InSAR data. But still work is needed to study all of these subsidence regions. If we place on top of that these triangles, what these represent is GNSS stations. These stations record how fast the land surface is moving up and down as well, but only in one site. And the things to note when looking at these GNSS stations is, one, their distribution is quite sparse. So there's a few in the northwest of the country, quite a lot in the northeast, but in the center regions, particularly in Tehran, there's not many stations recording the vertical change in the land surface. So it's quite hard to use these to really measure subsidence across the country. Secondly, the color of these triangles is kind of white mostly, which, looking at the color bar, this is how they're colored, shows the vertical subsidence rates they're recording are either not subsidence at all, it might be quite stationary, or going up, or they're really quite slow. This might be because, or probably is because, these GNSS sites were placed to record long-term tectonic deformation. Iran is quite a tectonically active country. It has really quite severe earthquakes, sort of magnitude 6, 7 at maximum. And so if you're wanting to record these signals, you wouldn't want to place your GNSS station on sort of quite rapidly moving sediments, which are subsiding. So one, this makes it difficult to observe where subsidence is happening. Two, it makes it difficult to validate any other measurement of subsidence, which we do remotely using InSAR, because there aren't many on-the-ground measurements of subsidence being recorded through GNSS. So going back to this map of well drill status, we place on top these polygons of subsidence observed using InSAR. We can see the polygons correlate quite well with the orange and red colors underneath, again highlighting the relationship between groundwater depletion and land surface subsidence. It would be great, however, if we had a better picture of where land subsidence was happening from building on previous literature, which is the aim of the studies we've been doing recently. Additionally, it would be great to better inform maps like this, and perhaps update the status of some of these planes based on the subsidence we observe using InSAR. So moving on to the methodology and results. First, we'll start with our Sentinel-1 InSAR time series analysis. So we began this work by building on previous work by Andrew Watson. His paper is in revision for this work. And so he produces velocity field on the left, which shows the surface and how it's moving. Is it moving up? Is it moving down? The deep blue areas show where the ground is moving down quite quickly, and the more redder colors are where the ground's moving up. This velocity field was completed to monitor and look at long wavelength tectonic deformation over the time series, not focusing on these subsidence regions. So it was a low resolution product, but it was really useful for picking out where these subsidence zones are happening. So we mapped where we can see vertical subsidence velocities exceed 10 millimeters a year over an area of 4 kilometers squared. And here they're outlined in these boxes, which you can see across the map. We then took these locations and adjusted the time series analysis parameters to reduce error and increase data coverage within these squares on the page. We also increased the resolution of the final time series products to 100 meter pixel width rather than 1 kilometer. So I think it was 500 meters, the previous product. So how do we do the time series analysis? So first, we take interferogram product from the COMET LiCS InSAR portal. So here's a picture of it in the right and the web link in the top right. This portal stores all the interferogram and coherence data and lots of the metadata for the interferogram products that you'll see here and other projects within COMET and LiCS used for their studies. We then use LiCSBAS, which is an open source InSAR time series analysis package that was designed to take as input these LiCS interferograms and conduct time series analysis. And this was written by you and Rashida back in 2020 and since been updated by people working on the LiCS project. So first we take all our interferograms and coherence products and downsample them all to 100 meters pixel width. Most of the interferogram products anyway are about this resolution, but some are higher resolution, so we make them all consistent and the same resolution. Next, we apply to each SAR acquisition a tropospheric correction using the GACOS or General Atmospheric Correction online service tool. So what this does is we download a sort of zenith path delay through the atmosphere, which basically means calculating how much the atmosphere interferes with the SAR acquisition, convert that into a line of sight path delay. So what is the delay in the line of sight of the satellite, and remove that from the interferograms. We then mask pixels in the interferograms with coherence less than 0.1. So the pixels are unstable and signal might be not too reliable. We then clip the unwrapped interferograms, which are now masked and corrected for, and the coherence products to the basin polygon extents, so those squares we saw on the previous slide. We then, this is the sort of data preparation steps on the left, and on the right we sort of begin the time series analysis. So firstly, we remove unwrapped interferograms from each sort of network by removing unwrapped interferograms if the average coherence across the whole scene is less than 0.05, and also if the pixels across that scene there's less than 60% coverage. We then continue to step 1.2 and conduct a pixel-wise analysis of these unwrapped interferograms and remove any pixels if the loop residual is greater than pi, unless all the loop residuals for that pixel are less than pi. We then conduct the small baseline network inversion and output static velocity fields and also time series for each pixel. These velocity and time series are in the line of sight direction. We then use bootstrapping to estimate the standard deviation of the velocity, and finally mask pixels based on noise indices. So overall, for the 111 subsidence regions across Iran, which we identified, we used 29 ascending and 27 descending frames from the LiCS portal and more than 77,000 LiCS interferograms to conduct this time series analysis. So the results of these time series analysis are available to view on the COMET subsidence portal, which you can access through this QR code. What this portal does, here is a homepage. There's a map in the top of this page, and each red circle, sorry, the light's going off, represents a subsidence region, which you can have a look at. All the text on this portal is available in Farsi and English, so we hope that people in Iran might be able to use this portal to see where subsidence is happening, if it's happening near them, and how can you mitigate against it. If you click on the regions tab, you can also select regions in this way. So if you click on a region, here we've chosen bar 01, which is near where that pistachio plantation was, which you looked at before. You can pick which frame you would like to look at, choose which data you want to look at. You can pick whether you want to view the atmospherically corrected data or the not corrected data. You can choose whether you want to view filtered or unfiltered data. Now this refers to a spatiotemporal filter, which can be applied during the time series analysis. I choose not to use this filter, but on this portal you can choose whether you want to use it or not and see the impact on the time series data. Now in the bottom here you can see a map with reds and blues, and so here you can pick in green which points you want to view on the right in the time series panel, and in red these are the reference pixels, so where you think there's no deformation, where the velocity is likely to be 0. You can also select to view the Sentinel-2 cloudless layer, so you can see what the land cover is like where you're viewing your velocities. You can also view a profile across the velocities in the scene. So this green line shows on the right the displacement that you're viewing, so you can see it's quite sharp in the center, where in the elevation behind it there's a valley. If you scroll down in the page, you can then choose some data to download. So you can download all the time series data as CSV files or also as HDF files, and again you can choose which level of filtering or correction you want to apply. As well, you can have a look and download individual interferograms. So going on a bit more, on the using the portal section of the portal, you can read more about how to use the data and what it means. As well, you can have some technical information questions answered. So for example, what we talked about earlier, how does groundwater extraction lead to land surface subsidence? And what is GACOS? And again, thank you to LiCSAR for helping me translate the English version of this text on the portal into Farsi. So once you have your LiCSBAS time series data, I said earlier we'd like to decompose the line of sight velocities into vertical and east-west velocities. We do that by using a tool called decomposed InSAR velocities, which was written by Watson et al. And it's available on GitHub, and it's written in MATLAB. And basically it takes as input the LiCSBAS time series data and outputs these two component velocity fields. So how does this work? First, we regrid all the time series data into 100 meters common grid. We then merge the velocities and standard deviations along track in preparation for the next step. We then correct for something called the reference frame effect or continental plate motion effect, which is sort of shown on the right in the diagram. So during the Sentinel-1 time series, our time series is 2014 to 2022, over 8 years, the continental plate, which your SAR is looking at, does move over time. And this can cause over the whole time series sort of a ramp across your frame in the range direction. So if you look at the center here, there's a blue to red ramp, which is quite gentle, but this can sort of add and remove velocity from your time series data. So this step aims to remove that ramp. We then tie the line of sight velocities to an interpolated north genus S field. Firstly, so that all the line of sight frames are in the same reference frame, but also to, looking at this equation on the right, input into this first equation as Vn, making it possible to calculate the Vu and Ve at the end, making the equation less underdetermined. So finally, we perform that velocity decomposition and output the vertical and east-west vertical velocities and what they look like. So here is a map of all the east-west velocities for these 111 regions across Iran. As you can see, there's quite sort of not very sharp features in these squares, so it's quite like gentle ramps in velocity, apart from some places. So in the bottom left, we've highlighted the Rafsanjani region, where you can see there's sort of blue and red north, west, south, east trending sort of velocities. And what this means is the red colour means moving east, the blue colour means moving left or to the west. So in these larger subsidence regions, you're getting some inward collapse into the centre of the subsidence region. Looking at the vertical velocities, here the blue is going down and the red is going up. And you can see a slightly better coverage of data in some region, particularly the northwest. And you can also see that in several regions the velocity over large areas exceeds 30 millimeters a year. So looking at the east in a bit more detail, the east-west velocities, we put behind those subsidence velocities on the left the original velocity field produced by Watson et al. You can hardly see the subsidence velocities in the right-hand image. This is quite surprising to me when I first did it, but it shows that the east-west velocities are dominated by the regional tectonic deformation signal rather than the short wavelength subsidence signal, which we can see really clearly in the vertical velocities. So on top of in the right-hand panel is the active tectonic faults in the region. And you can see some of the east-west velocities correlate quite nicely with these faults, particularly in the northwest. So you can see that red eastward motion separated from the more southern westward motion around Lake Ermia, which is quite nice. So if we zoom in, that's a reminder. This is of the pistachio farm we looked at before, and where we're going to have a closer look now. So here are the vertical velocities around a pistachio farm, where that red dot is, which we were looking at before. These are outlined by this grey line, which is showing you inside where velocities exceed 10 millimeters a year in the vertical direction. And this is the map of the east-west velocities for the same region. You can see there's quite a lot of detail in those east-west velocities, not linear and straight necessarily. They have some curvature to them. This pattern might be due to underlying sedimentary features in the sediments, or potentially some fissures or faulting within the region. We look at the profiles of the velocity. So along the line A to A dash, A is on the left hand of this plot to the right, and A dash on the right. You can see the peaks of subsidence align with the valleys in the elevation profile, which is expected as this is where the sedimentary grains are deposited when there's high erosion rates, and you get the sedimentary basins. On top of that, if we plot the east-west velocities, you can see in the middle of these subsidence peaks, the east-west velocity switches direction. So particularly on the left-hand side, you can see there's a sharp increase in east-west velocity and decrease as the peak of subsidence is reached, which is what we expect if the sedimentary grains basically fall into each other in the center. If we plot on that the active faults I mentioned earlier, you can see that some of these faults bound the subsidence bowls, particularly on this faster one on the right-hand side. On the left-hand side of this subsidence bowl is really controlled by where that active fault is located. However, at the moment, there's no active faults mapped in the center of these subsiding regions. This might be because there aren't any, or it might be because we don't see any evidence for them at the surface, because sediments have been deposited on top of fault scarps that you might expect to see in the field or in digital elevation models. So perhaps these east-west velocities combined with the vertical velocities can help us get a better idea of where active faults might be located and buried underneath active deposited sediment. So to summarize the slide, land subsidence in Iran is constrained mainly to valleys and sometimes by mapped tectonic faults. If we compare this subsidence to land cover, so on the top right here, this is a map of land cover in Iran, divided into 13 classes by a group at Tusi University of Technology in Iran. This is a great map. It's basically made by mosaicing Sentinel-1 and Sentinel-2 images across the country and using a random forest classifier to classify each 10 meter by 10 meter pixel into a different land cover. Now on the top panel here on the right, you can see the outline of subsidence of 10 millimeters a year. It's a grey line on the left, it's now on the right in white. And within that polygon, you can see mostly the colour is that sort of grey-blue colour, which is farmland. And if you repeat this sort of analysis across all the subsiding regions, you get this histogram here. And what this shows is an overwhelming amount of blue in this bar chart, showing you that 70% of the land subsidence we observe using Sentinel-1 InSAR in the study is on farmland, which is probably expected because this might be where groundwater is being extracted for use in irrigation on the agricultural land above it. But is a bit in contrast to other countries around the world where subsidence tends to happen more in the cities where these wells are more preferentially located, for example, in Mexico City. Moving on to look at, we can compare this subsidence that we observe with InSAR to that predicted by Herrera and Garcia in 2021. So we looked at this map on a global scale in the earlier slides, but here is the same map just for Iran. As a reminder, the yellow, orange, and red colours here show us where there's the group have predicted there to be a medium high, high, or very high chance of subsidence. And you can see quite starkly on the northern coast of Iran, so on the southern coast of the Caspian Sea, there's quite large areas of red, and across the country there's other areas of yellow and orange. So how does this compare to our observed subsidence? So here are all the areas on this map that are yellow, orange, and red, just all coloured in black to show us where subsidence is expected to happen based on their predictions and model of subsidence potential. On top of that, we plot in yellow where we observe subsidence to happen faster than 10 millimetres a year using our InSAR data in the vertical direction. On top of that, in red, we plot where the two data sets, so the high subsidence has a potential and the vertical velocities exceeding 10 millimetres a year overlap. And you can see quite clearly there's a really good overlap between the two data sets. So on the whole, 83% of the time where we see subsidence using our InSAR data, the incidence of this subsidence was predicted by this group in their model of potential subsidence. However, there's other regions which stand out to be quite black on this image where we don't observe subsidence. So let's look at these in more detail. So one example is here along the south coast of the Caspian Sea, which I mentioned was quite bright red in the predictions of potential subsidence. So let's have a look at the InSAR data in more detail. So on the bottom right here, we've got this region around the city of Rasht, and you can see there's a lot lower coverage of InSAR data, so fewer pixels of data compared to where we were looking before. Additionally, you can see where there are cities in these orange circles, there tends to be sort of light orange color to the velocities we observe. And around these cities, we see more of a blue color, and it's more patchy cover outside of these cities. So why is this? If we look at that land cover product we were looking at before, and lay our subsidence velocities, those vertical velocities, on top of this land subsidence, we can see that where we don't get coverage of InSAR is where there's more marshland land cover. Now, marshland is sort of a watery, vegetated land cover, which is quite difficult to image using InSAR because it tends to be unstable and incoherent, which might be one reason why we don't get data here in these gaps in spatial coverage. Additionally, and I'll build on this later, you might tend to observe more frequently the occurrence of fading bias, which is essentially due to the vegetation cover and perhaps changing soil moisture in these regions, a bias that accumulates in these sorts of land covers and can add a non-real signal in the vertical direction, basically meaning any substance you observe here might have an additional error added to it, a non-real substance signal. And so because the substance velocities we observe here are not as fast as other regions across Iran, and where the subsidence is sort of observed to happen, we don't get, this is marshland. We've decided not to class these regions as reliably observing subsidence here because one, of the fading bias, but two, the coverage is too low to really assess if these regions are subsiding or not. So despite there being patches of really quite fast subsidence, I think here subsidence reaches about 50 millimeters a year. We're not too confident in classifying these regions as subsiding on the whole. So to summarize our subsidence velocities section of this work, we use previous work to identify 111 subsiding regions across the country. We then use 77,000 LiCS interferograms to construct surface velocity fields for these regions. And we find subsidence velocities exceed 150 millimeters a year in 13 of these regions. So going back a bit further to talk about angular distortion relating to these subsidence velocities, remember that angular distortion is essentially a measure of the subsidence velocity gradient in space. Can we work out what this angular distortion is for our subsidence regions? Well, we've attempted to do so. So in the InSAR data, as we mentioned before, we're looking to calculate the differential settlement over the time series over a length scale, here the pixel width, which is about 100 meters. Now, this sort of analysis has been done before. For example, here, this is a map of Mexico City. On the left, plots angular distortion. On the right, this angular distortion has been classified into surface faulting hazard. And you can see on this map, behind there is red mapped faults and cracks plotted on top of angular distortion in deep black. And you can see angular distortion really correlates quite well with those mapped faults and cracks. So angular distortion could be quite a good proxy for mapping faults and cracks in the field. So let's look at Tehran. This is the capital of Iran in the north of the country, and it's really quite densely populated. If we plot our subsidence velocities on top, so the vertical component of our velocities, you can see that Tehran itself and Karaj, another city to the west, their centers are located away from these subsidence bowls. If we then calculate angular distortion for these regions, you can see it's confined the highest rates to where the subsidence was observed by InSAR. So in this white dotted line, this outlines the subsidence polygon we were talking about before in these regions. You can see the highest rates of angular distortion observed near Karaj city rather than Tehran. But something to note is, so we use quite 100 meters resolution sounds quite high, but sometimes these gradients can be quite steep in a shorter wavelength. So perhaps our method averages the angular distortion gradient a little bit in that pixel, and we might be missing some of the steepest gradients of subsidence using this data. If we then classify this angular distortion into those surface faulting hazard categories, we can see that there's some patches of medium surface faulting hazard and sort of one or two patches around Karaj of high surface faulting hazard. We don't actually get here the very high surface faulting hazard that other maps in Mexico City plot. That might be due to the resolution problem I mentioned in the previous slide. However, what we can do is here we use the World Pop dataset to map population density across this area. So this sort of dark grey colour behind the data, this maps where the population density exceeds 15 people per pixel. So 15 people per 100 by 100 meter pixel. And you can see mostly some of the yellow areas are more in farmland areas, especially to the south of Tehran. But the highest surface faulting hazard is located where there's a quite high density of people. So we can take this a step further and add up the number of people exposed to surface faulting hazard of different levels in each category. So doing this, we can see that in this region mapped here, 114,000 people are exposed to medium surface faulting hazard, and around 10,000 people to high surface faulting hazard. So this sort of analysis can be expanded across the whole of Iran, and we hope to do that in our next work. So moving on to our final section of fading bias, or fading signal. So I mentioned this before, but what is this phenomenon? So those who work in InSAR might be more familiar, but this bias is a non-zero signal that's not due to deformation that accumulates, particularly multi-look short baseline interferogram networks, which is what we're working with here. So for example, this plot on the right was produced by InSAR et al. In 2021. And on the right is a velocity field calculated using longer temporal baseline interferograms, on the right with shorter temporal baseline interferograms. And you can see a greater substance velocity is calculated in the left-hand image. So basically the structure of your interferogram network and the length of your interferograms can affect the observed signal you see due to this bias. The cause of such a signal is a subject of active research, but can include vegetation interference, so the interference of the radar signal from the satellite with the vegetation, or soil moisture changes in the ground. And it's assumed that interferograms of sort of 6 to 12 days contribute most to this signal. So as we've seen before, lots of the subsidence regions we're looking at are covered in vegetation and probably liable soil moisture changes due to irrigation. So we test the impact of interferogram length on our vertical subsidence velocities. So here we look at the northwest of Iran, where there are these 2 LiCS interferogram frames. And we look at this region because 1, there's a really great density of interferograms here. And 2, this is quite a vegetated region of Iran and a more wet region on the ground. So it's a good place to test sort of the maximum fading bias signal we're likely to observe. So we look at these 2 regions highlighted in red, Lake Urmia to the south and Marand to the top. So on the top here, we have this frame, which starts with 174A, the ascending frame. Its network and all its interferograms we use to calculate our final velocities on the top panel. In the middle, these are interferograms less than 25 days in length. On the bottom, those more than 97 days in length. So we test sort of a combination of different length interferograms between these 2 M members on the bottom half of the slide and see what the impact is on our final velocities. So here are the results. On the top sort of panel, you can see all the different lengths of interferogram networks in combination with the results. And the bottom left, you can see a profile of these velocities profiled across A to A', which is shown the location of in the less than 97 days panel. So what you can see here is maybe what you expect. The sort of greeny cyan colors are those shorter, are those networks with shorter length interferograms, and subsidence velocities here are quite large, so up to minus 70 millimeters a year, so vertically 70 millimeters a year subsidence. But where we use longer interferograms, so for example, more than 25 days, you get sort of a drop in peak velocity of 50% or so, which is reassuringly similar to our all situation, so using all those interferograms. If we look at the other region we were analysing, Marand, you can see it's a similar situation. So you do get a peak of sort of 80 millimeters a year from a few pixels in that 97 days, less than 97 days network. But roughly half of the peak for the longer interferogram networks is roughly half of that. So what we can conclude from this is we can reliably say where subsidence is happening across Iran, but potentially, depending on the network structure, the absolute velocities and peak velocities need some careful consideration before working with them more widely. So to conclude, we use Sentinel-1 InSAR data to map subsiding region extents across Iran in 2 components at 100 meters resolution for the first time. Land subsidence in Iran is most prevalent in valleys filled with agricultural activity on young sediments. And for the first time, we calculate the occurrence and the number of people potentially impacted by high surface faulting risk due to differential land subsidence rates in Tehran. And finally, we assess the contribution of fading signal to these vertical subsidence velocities in Iran could be up to 50%, but we need some further work to confirm this conclusion. In future, we hope to update the substance portal. So at the moment we have 99 regions on there, but recent work we've identified 12 more, and we'll update the portal in due course with these regions. As well, we'll try to upload the component velocities. 2, we'll expand our surface faulting risk assessment to other major cities in Iran, and also expand our assessment of fading signal to absolute subsidence velocities. Finally, we'll compare and correlate InSAR deformation data with groundwater loss estimates from gross gravity satellites and local groundwater level data. So thank you for listening, and it would be great to hear your questions.
Thank you very much, Jess. That was a really interesting talk. It's also really good to see that you've got data available, and with having things in multiple languages, I think that's a really fantastic output. So yeah, well done.
Thank you.
We have some questions already in the Q&A. If anyone else has any questions, please ask them now. I think we're approaching when we would usually stop the webinar, but we'll keep going for a bit. But if anyone has to go, I'm sure Jess would be very happy to accept questions by email as well. So our first question is from Matthew McKinnon-Bell, who says, I've really enjoyed the talk so far. I was wondering what method you used to determine which pixels were noisy in the analysis earlier, and whether different methods of determining that would lead to different pixel maps as a result.
Yeah, so generally there's about, I think, 12 or something indices we use to mark pixels, including one I mentioned, coherence, things, for example, loop closure error. So people with InSAR will be more familiar with that. There's other measures, for example, standard deviation, which I mentioned, others which I can't remember off the top of my head. But yeah, using different thresholds for these sort of masking indices would definitely lead to different pixel maps. But we've tried to use a combination which doesn't let in too many erroneous pixels, but also allows us better coverage. So one thing that we've done differently to the previous ground velocity field, which I showed earlier, was have a different method to remove noisy pixels, which means our loop closure error is lower. So as well as sort of increasing coverage, we've hopefully removed more erroneous data at the same time. But yeah, you're right, it'll lead to different pixel maps.
Great. Our next question is from Ekbal Hussain, who says, great talk, Jess, well done. Have you thought about the impacts of other sources of subsistence, for example, building loads?
Yeah, so this is something I've thought about. I did do some analysis looking at, one, does the land cover affect the rate of subsidence? And two, where is this subsidence happening? Is it happening mostly in cities, or is it in agriculture areas? From the first sort of mini study, the sort of land cover doesn't really affect the peak or distribution of velocities. So that sort of leads you to think that building loads might not impact subsidence rates too much. I mean, they might at a local scale, but on a countrywide scale, not so much. It's difficult to determine. And yeah, looking at land cover, you can see mostly we're looking at agriculture areas. So something else to note in this, so thinking about this, is we're looking at 100 meter pixels width, which is perhaps too coarse to look at whether building loads are affecting subsidence rates. If there was a really large development, say a large industrial development exceeding sort of a few hundred meters width, you might be able to look at building loads impacting subsidence, but perhaps in this method, it's not something we can assess too well. Perhaps PS InSAR would be better.
Great. Our next question is from Surasha Yassini, who says, I am working on land subsistence measurements with LiCSAR product. Is there any way to participate on this program for studying land movement in other cities of Iran?
Yeah, definitely. If you get in touch with us, my email's on the screen. We definitely be keen to work together and see what work you're doing. So yeah, please get in touch.
Fantastic. Our next question is from Ibrahim Barry, who says, in two of the maps you showed, it seems as if Africa, South America, and Australia are relatively less prone to land subsidence. Are there any specific geological explanations for this?
So I'd say I don't know too much geology about all of these areas, But Australia, I know there's quite a really old basement to it, so really old bedrock and not many deep, thick, young sediments across the country, unlike in Iran, where there's quite young mountain belts in geological time, and quite a lot of these are eroding quite quickly in recent geological time, so you get thick sedimentary basins accumulating. In Australia, I don't believe it's the case. South America, I'm not too sure about that one. Need to look it up in more detail. Africa, to be honest, there's quite high subsidence rates in places like Lagos in Nigeria, and I don't know whether, yeah, it might be a sort of understudied region as well as it's not less prone to subsidence. I'm not too sure, but yeah, I'm not too clued up in the geology of Africa either.
Okay. Our next question is from Amir Abu Hassan. Sorry for my bad pronunciation of people's names. Who says, thank you for the nice work and presentation. The longer time series of greater than 90 days concludes smaller subsidence field. How do you interpret this?
Do you mean, if you mean less data coverage, or let me get back. So more than 97 days is smaller. Smaller subsidence fields. So yeah, if you're using that threshold of more than 97 days, you do get quite a fewer interferograms compared to other networks, and so then this can impact sort of the density of pixels you get in your final velocity field. So yeah, that's one thing to note, that which I didn't mention. If you're looking at these maps on the screen, the pixel coverage in all of them is slightly different, so you're not exactly comparing like for like all the time. Perhaps the subsidence you can see in short time series. Yeah, potentially some of the subsidence in short time series is compensated by uplift. I don't know how much that uplift can be caused by precipitation, as in how fast this can be and what the maximum magnitudes can be. But you could get some seasonal uplift over time. But if you look at the long-term trend, it is generally down with a seasonal component to it. So generally precipitation leads to sort of a short-term uplift, which is then again exceeded in the next drier season. What is that processing effect? Yeah, there could be some sort of processing effect in this as well. I mean, these are quite recent results. We sort of think about them a bit more thoroughly. But yeah, it could be some artifact processing.
Great. Our next question is from Astaj Fassad. Do you plan on processing the full resolution, so 20 by 5 meters Sentinel data, to derive more accurate angular distortion values?
That would be great, and it could be something we do. So some of the frames we work with, we already have data at sort of about 56 by 56 meters resolution. Generally in sort of the COMET workflow, we don't work at those lower resolutions, but it's something we could do to definitely get more accurate angular distortion values. I think it would be a valuable output from this work as well. So it perhaps should be something we prioritize.
Okay. Next question is from Adrian Maga-Basaka. It says, thank you for your good presentation. My question is, how many images were used and how many interferograms? So
I think I showed earlier about 70,000 interferograms or individual SAR images. I'm not actually sure. Sorry about that. And we used GACOS. So GACOS product, from the top of my head, I think works as GACOS uses ECMWF data, so the European Weather Service, I think, to calculate delay of the radar in the line of sight direction due to atmospheric noise in the troposphere. And then we convert that so zenith is looking up down. We convert that path delay in the vertical direction to a line of sight direction, which Sentinel-1 is looking at that place at that time, and then take that delay away from each acquisition, so each SAR acquisition. I hope that answers your question.
Great. We have a question now from Farnaz Kamransad. He says, thank you for your interesting presentation. Just out of curiosity and from a seismological perspective, is there probably any evidence of correlated seismicity with stress redistribution and subsidence in Iran? And are there observable patterns of shallow seismicity or earthquakes, swarms and clusters triggered by such subsidence?
Yes, that's a really interesting question, and something you sort of do observe with oil and gas removal, especially in the US. You see like increased seismicity due to fracking and things like that. But in Iran itself, I haven't looked at sort of the microseismicity, the low magnitude earthquake patterns, to see if they're correlated with subsidence. But there might be studies out there that do this. And it wouldn't be too surprising, I don't think, if you get this sort of pattern. But yeah, that's a really interesting result.
Fantastic. Our next question is from Charles Forrester. So, who wants to know how you're differentiating between movement due to groundwater as opposed to background tectonic activity?
Yeah, so that's a great question. And I think in the vertical component, so these deep blue colors we can see on this slide, the tectonic motion generally is a lot smaller, is a long-term tectonic deformation than the subsidence signal. So we tend to just not correct for it. However, if there's an earthquake in our subsidence scene, we'd deal with this in a different way. So currently I haven't seen any earthquake signals within our time series within the subsidence regions. There's some sort of outside it. But if they interfered with each other, we would do something to correct for this. Yeah, but in the sort of east-west velocities, you see more of the long-term tectonic deformation trend, and the subsidence signal doesn't really overprint on this too much, apart from the short wavelength, so it's sort of the 100-meter scale, and they look quite different signals. So they might interfere, but the two look quite distinct. So we don't really correct for it, but we can sort of see they're different, if that helps.
Okay, I have a question from Musavi, who says, thanks for a nice presentation. As I remember, there are more GNSS sites that are presenting subsistent occurrences in Iran. And also she can mention that the GN site located in Gorgan City, east of the Caspian Sea, you may be able to use this area for where you have no reliable InSAR data.
Okay, that's really great. Thank you. I've written that down and we'll look into it after the presentation.
Great. So I have a quick comment from Ibrahim Barry, which is a compliment, just saying a nice and educative presentation on land subsistence, and thank you, which I will second. Was a very good talk.
Thank you.
Okay, next question from Reza Ramhipur. Hello, thank you for this amazing presentation. I have a question about critical baseline. Does this have influence on the results?
I'm not too sure what critical baseline is, sorry, but if you want to type in the box what you mean by that, I'll happily answer your question.
So we'll go on to the next question now, which is from Noah Medhat. It says, thank you for an interesting presentation. Was the phase closure filtering considered in the analysis?
So if by that you mean masking pixels based on phase closure error, so like the residual after you calculate the phase between like triplets of pixels and interferograms, that was used as a masking parameter in the time series analysis step. So pixels with a large phase misclosure we did discount from the analysis.
Okay, great. Next question from Maraz. Great talk and presentation. How do you validate the results of your fading signal estimation to decide what is the best interval?
Yeah, so that's a really good question, and something that's difficult in this region, as you saw, because of the sparsity of GNSS data and outside sources of measuring subsidence rates. One thing we can do is try to use methods that try to correct for fading bias, which are being developed as we speak. But deciding which is best, I'd say, is difficult and something that is being researched by many people in the InSAR field. So yeah, I'm not sure how to answer that question at the minute, but it's ongoing research.
Okay, probably coming to our last question now. Oh, we're getting a few more coming in. Thanks. This is from Sureshi Asini. Thanks for answering previous question. Another question came to mind. Why were there no north-south movements measured?
So this is because the satellite we're looking at, Sentinel-1, and many other satellites orbit the Earth in sort of nearly north-south direction. So it's called like a sun-synchronous orbit. And this means as the satellite's moving north-south, it's quite difficult for the satellites. It's quite insensitive to north-south motion. So of the line of sight signal that it records, I think about 0.1, so 10% of that signal is due to north-south motion or something like that. Sorry, that wasn't a very technical response, but basically Sentinel-1 InSAR's not very sensitive to north-south motion. So we can't really derive it from the line of sight using this method, but there are other methods which you can derive north-south motion, not with this pixel coverage, but it's called sort of burst overlap method, which some people here at Leeds are working on to calculate north-south motion, for example, in earthquakes, like the Turkey one, which was earlier this year. But on a large scale, like across our subsidence regions, you can't get a great coverage of north-south motion from Sentinel-1 InSAR due to its orbit.
Okay, and now our final question from Sami, who says, thank you for the nice work and presentation. Have you looked at the east-west component of deformation in subsiding areas? And is there any correlation with the angular distortion?
So yeah, we've had a look briefly at the east-west component of deformation, and there probably is some correlation with angular distortion, but you can use the east-west component to also calculate something similar to angular distortion, the name of which I can't remember off the top of my head, but it's something I aim to do in the future, is look at sort of the gradient of east-west deformation as well. So it might, and that'd be great to see if that correlates with angular distortion.
Great. We have one comment from Adrian, who says, again, thanks for a nice presentation. And then maybe it's possible to create a network where we can share experiences, ideas, add more presentations on land subsistence.
Yeah, I mean, that would be great. I think there is an international land subsidence committee, which is sort of attached to UNESCO. So if you Google TSOLs, for example, that was a conference I went to earlier this year, which they ran, and UNESCO, that will come up. And they have lots of resources about land subsidence, which you can have a look at. So it's like a global network.
Excellent. Okay, I think we will finish there. But before we finish, I want to remind everyone about the next COMET webinars on the 6th of December, which is going to be given by Ben Essie, and hopefully some of you will be able to make it. And another reminder that you can access many of the previous COMET webinars on YouTube. So thank you all for coming and for asking so many questions. And thanks again to Jess for a really great talk. So yeah, thank you very much.
Thank you.
Thanks, Jess.
Bye.
Great presentation.
Thank you.
That was very good engagement, Jess.
Yeah, that was really
a
nice.
Fantastic talk.
Thank you very much. No, it was really nice to get so much interaction. And yeah, thank you for facilitating the webinar. It was great to share what I've been doing. Yeah. Cool. Yeah, I might sign off there, but yeah, see you guys soon. Yeah, good luck with the future webinars.
Yeah, see you. Thanks.
Thanks. Bye.
Bye.
Bye.